So welcome back, everybody. And this is our, in a way, last regular session. Next week, we will discuss more the projects, but there may be things which will drift over about the classical Boltzmann machines and the quantum Boltzmann machines. So you can look at the Boltzmann machines as a kind of, just as a teaser, as an excursion into a topic which is very popular with quantum machine learning. Now, today's lecture is going to be, since we did not discuss codes last week and the week before, the idea now is to focus a little bit on the quantum neural networks and how we implement them. In particular, I'm going to discuss this topic which deals with the natural gradients and remind you of some of the topics we discussed last week, because last week I showed you something which is called stochastic reconfiguration, which is used in variational calculations, especially variational Monte Carlo calculations, which is a very efficient way by which we can implement the so-called Hessian matrix, which is an approximation to the second derivative. And we are going to bring up some of these arguments. So I wanted to say a little bit more about the natural gradients and how they pop up in the machinery. So if we get time in the second lecture today, we will start with classical Boltzmann machines and point to quantum Boltzmann machines. But I wanted to go through things which we did not discuss properly last week. And one is the coding examples with applications both to a simple regression type of problem where we fit a polynomial, but also where we solve a differential equation with so-called PINs, physics-informed neural networks, but on a quantum in a quantum machine learning context. And the equation which I'm going to use is the same which I used in connection with the HHL algorithm, that is the Poisson equation. And we are first going to show how we can implement that with the standard hybrid approach, where we have a classical optimization part, and this can be done by Broyden's method or alternatives to Broyden method, or we can use an optimizer like Adams. So in the codes, you will see a quantum pins solution of the Poisson equation in one dimension using Adams, but then we are going to show how you can use the natural gradients. The natural gradients are also interesting in connection with what is called the quantum Fisher information, which in a way expresses the covariance of the score function. So what I want to do now is just to bring up the slides from last week and remind you of some of the topics which we discussed last week. So let me just bring that up again, and then we are going to switch to back to the whiteboard. So let's take a quick look at what we discussed last week. And let's increase this to the full screen. So one of the things which we discussed last week was actually the input coding. And then we try to motivate this link with the fish information. And this is something which I want to catch up again today. So basically, a quantum neural network contains one operation here, unitary operation, which is essentially an application of X gates, rotations, which then encodes the classical input. Then, so this is fixed. And we had 4 different ways of doing the encoding. The examples which you will see are very simple cases where we use just a few qubits, because this is something which is easy to run with the Jupyter-notebooks without taking too much time. So we will have 2 or up to 4 qubits, so it's not an impressive amount of qubits. But you will see that even with that small amount of qubits, our quantum neural network is going to do a better job with fewer parameters than a larger standard machine learning approach like a neural network. So there is a feature map, and then there is the variational ansatz, where we have the trainable parameters. And the variational ansatz contains a set of Pauli rotations, X, Y, Z, and you can make this as deep as you want. So just to quickly remind you of the connection with neural networks, these different variational ansatz components, like a CNOT gate, the rotations, etc., they become the variational parameters, which we then train in the standard optimization. And in one of the examples, you will see that we are using some 20 plus rotation gates on 2 qubits. And that's going to give a pretty decent result for the optimization of a fitting of a polynomial. Then, since we are dealing with Pauli rotations, then the parameter shift rule can actually be used, and it's going to be exact. So we have an exact expression for the gradients as a function of the parameters theta. And then finally, there's a readout, the observable. Now, one of the things which I wanted to give you some more information about, and you will also find information about that in the additional material which we have on the Fisher entropy. And this is a quantity which many of you will encounter, in particular if you're looking at quantum sensors. The quantum Fisher information is a quantity which pops up again and again. And it's actually given by the covariance of the derivatives of the score functions. And coming back to that. So the typical approach, which we then need to deal with after we have discussed this, is then the input encoding. And the encoding is actually part of the model, and choosing it well is as important as designing the variational ansatz. For PDEs, the encoding also determines which spatial frequencies the circuit can actually evolve. So in the example where we solve a partial differential equation, the type of encoding actually plays an important role. So the thing which we discussed last week was a kind of first a brute force encoding, where we simply map a binary string to a computational basis states. And clearly, this is something which we, as we discussed last week, requires a set of gates, and it requires n qubits for n bits. So clearly, if you have lots of information which you want to input, this becomes not very feasible, and it's also not suited to continuous features or PDEs. So the alternative is something which is called angle encoding, which is widely used. There's a 1 feature per qubit. There's a product state. There is no entanglement yet, it's just a product state. So typically, when you look at the way you encode the unitary feature map, is that you don't have an entanglement in that one. So the entanglement is something which you would plug in the variational ansatz. So that means that normally the U of X, the feature map encoding or the encoding of the input, is something which you would simply set up as a product of various rotational states. So this is typically the one which you could see here. And it's no entanglement. You can have entanglement added by these are added by 2 qubit gates in the variational part. And the output then is a Fourier series in X with frequency determined by the generator spectrum. So this could be something you could use for the solution of differential equations. So amplitude encoding is also another way of doing this. And the bottleneck here is actually the readout, because the exponential compression does not automatically give a speed up. And reading out all the 2 to the n amplitudes requires exponentially many measurements. So this is normally the fundamental quantum readout bottleneck, which is relevant to, for instance, if you're dealing with quantum physics-informed neural networks. So this is also used in the studies of quantum physics-informed neural network, amplitude encoding or angle encoding. And then there's something which is called the structure feature map, which is something which, for Q-pins, for instance, quantum physics-informed neural network introduces cross-frequency terms that enrich the Fourier spectrum of the solution approximations. So this is something which I have not tested myself. So I would just refer to the literature here. And if you're interested in looking at it in more detail. So I have not tested the structure feature map. And there are many other ways of doing this. And typically, what you would need to do then is simply to run numerical experiments where you try different ways of encoding the input. So this is one big issue actually in the setup here. Now, one of the things I wanted to say a little bit more about is the calculation of the gradients and the so-called Hessian, and this related to the second derivative and this quantum Fisher information. So in the weekly material this week, I have added some notes on the Fisher optimization or the Fisher matrix, and I wanted to bring that up before we dive back into the codes. So the quantum Fisher information is actually a very important property, and what it does, and we are going to come back to this derivation, where it comes from. So what we have is a geometric meaning, which means that we have a metric where we can optimize, and this measures from a quantum information point of view or information point of view, it measures what's called the information geometric distance between neighboring quantum states. And it's actually related to the covariant of these rotational circuits. So, but let me go back a little bit to what we discussed last time. And I'm going to go back to the whiteboard and remind you of some of the topics which we discussed last week in connection with stochastic reconfiguration, because what we end up with is actually a problem where we are optimizing the parameters using what's called the natural gradient. In the Jupyter notebook from week 15, which we are going to bring up, we are going to actually compare the calculation of this quantity, the Fisher quantum information, with a standard Adam method where this one is just replaced by a parameter, which is updated in a primitive way by the gradients, and Adam is one of the optimizers. And then we multiply with the gradient, which we can calculate for these quantum machine learning algorithms. We can calculate this one exactly with the parameter shift rule. So that means that we have the same circuit, but we simply call that circuit several times because we need a gradient with respect to an angle pi half and minus pi half. The thing is, why do we care about this natural gradient? And I will try to explain to you why this is actually an interesting quantity to implement. And this natural gradient is also, or the quantum Fisher information is also related to the derivatives, the expectation value derivatives and the expectation value of the cost function, which then can also be linked with the quantum Fisher information. And that is something which links again with the barren plateaus. So in principle, the functions which we are optimizing are normally convex functions and well-behaved. However, we may get stuck with the derivatives which actually go to zero faster than we would like to. And the way these behave is actually something which is proportional with the number of qubits, where this 2 to the n is a number of qubits. So that means that we can easily get stuck in a barren plateau in the optimization problem. So I'm going to switch now back to the whiteboard. And we are going to look a little bit at some of the topics we mentioned last week, and then put that in connection with this Fisher information. So let me just bring up the notes here. So one of the things which we looked at last week was the optimization of the energy. And what we had was a quantity which we defined as the logarithmical derivative of the trial wave function. So if you think of what we're having, so if we look at this quantity here, this was defined as psi, and psi depends on the optimal parameters theta. And then we had the derivative of psi as a function of the optimal parameters, and the derivative with respect to the parameter theta. And this is something which we could write out as the log of psi. And now I'm going to skip in some of the notations here. I will skip x and the x and the theta dependence of the k, the theta k here. Now, what we defined then was the covariance of the log derivatives and this covariance is something which we labeled as an Sij. S is going to stand for stochastic reconfiguration, which is used in this kind of Monte Carlo type calculation or variational type of calculation where we actually, at the end, in order to calculate expectation values, we are going to sample with some Monte Carlo algorithm, where the sampling rules could be something like given by Metropolis algorithm, or we could use something which is called Gibbs sampling. So that is a covariance. If you want to remind yourself of the covariance, so the covariance of, let me just write this out here. Now, just to quickly remind you, the covariance of two variables, xi, xj, is given by the probability of p of x, sorry, xi dxj. And then we have the probability of xi minus, and we're assuming now that we can have a different mean values, and this is multiplied with xj minus x, the mean value of xj, and multiplied with the probability xi xj. This is the formal definition of the covariance, and if these are independent and identically distributed events, then the probability which you see here, that reduces into the probability of xi and xj. If they are independent and identically distributed, then this mean value is equal to that one. And if that is the case, then the covariance, if I is different from j, is exactly equal to 0. So this is just a quick reminder of one of these concepts from statistics. And what we did last time was also in the optimization part. What we had then was a quantity which we defined as the local energy, which depends also on this parameter theta. And this is defined as 1 over psi of x of theta. We have a Hamiltonian which depends only on the spatial degrees of freedom and other degrees of freedom, like spin, multiplied with this psi x of theta. This is a standard procedure if you're dealing with the variational Monte Carlo calculation. But it is also pretty close to what we have seen with the variational quantum eigensolver, because the variational quantum eigensolver is also a variational optimization problem. Now, what we can do in this case is also to define the gradient of the energy. So the energy then, the expectation value of the energy is actually given by the expectation value of this quantity. And what we need then in the optimization part is a gradient of the energy, which is then given by 2 times, and this is again the covariance with the local energy. So we would have this logarithmic derivative, and then we have the local energy minus the expectation value of this local energy, which is the energy, and this logarithmic derivative. And then the optimization problem, theta, the optimization algorithm, in order to find the optimal theta, contains theta minus, and then we have the inverse of this matrix multiplied with this gradient g of I. It contains an additional parameter, which is an imaginary time step, delta tau, which we can use as a small parameter, which can typically be 10 to the minus 1, 10 to the minus 2, etc. This is the algorithm which now follows the form of the wave function. Whereas in a standard gradient descent, what we had then, and this is one of the examples we have in the lecture notes. So standard GD, what we have then is that this theta is being updated using a simple algorithm where eta is in machine learning and in the optimization literature is actually called the learning rate. And this is then given by the gradient. So we should put arrows over here because these are quantities which are vectors. And this is the standard optimization where this eta can be set up in different ways. So you can just have a fixed constant, or you can actually use an optimizer like Adam. And in the lecture notes, in the Jupyter notebooks, you will find examples where we have implemented the Adam optimizer for this learning rate in the neural network implementation for physics-informed neural networks. Now, why? So this was one of the things we discussed last time. Now, there's one thing I wanted to bring up, because this becomes also of interest when we are looking at quantum Boltzmann machines. If you look at a neural network, this falls under the general category of discriminative methods. So what does that mean? So a discriminative method is an example of where you make a fit to some data, and then you want to use that to make predictions, and you want to discriminate between different types of events. So suppose you train your model, a neural network, to recognize paintings of Munch. So this is what you've trained it on it, and it's a typical yes-no type of problem. So it's a binary type of problem. Yes for a Munch painting, no for something else. And then when you train the model, you would then feed in a new painting, which was not included in the training. So this could be a Van Gogh painting. And then the model you have made with a neural network, when you trained it, should then be able to tell you whether this is a Van Gogh painting, whether this is a Munch painting or not. So then we say that we discriminate between different types of painting. So in general, a neural network does not give you a probability distribution. However, you can, if you're using what's called in statistics a frequentist approach, you can actually generate confidence intervals, etc., by training a neural networks many times. Now, in cases where you solve a Schrödinger's equation with a neural network, this means like a quantum physics inspired neural network for solving Schrödinger's equation, then a neural network becomes actually a generative method because you generate a solution, and that solution can then be used to define a probability distribution. And we know that in the case of quantum mechanical problems, when we find the wave function, we can then square it, and then we have something which is to be interpreted as a probability distribution. So for neural networks, there is actually many of the deep learning methods, there can be a floating distinction between discriminative or generative methods. So when we think of a Boltzmann machine, which we will discuss a little bit later, then for a Boltzmann machine, that is a clear example of where we train a probability distribution. So let me bring up some of the elements, because these are elements which we will use a little bit later when we start with Boltzmann machines. So typically, when we now look at generative methods, so keep in mind that a neural network can also act as a generative method. So when you generate a solution to a differential equation, that can be used to define a probability. However, in general, most of these classical deep learning methods like neural networks, convolutional neural networks, are then more thought of as discriminative methods. So, but let's now do that. So we have a domain of events, which we could now define in terms of variables x1, x2, etc., up to some x of n. And there is a probability. So these x's, x of I, they are drawn from a probability, which we simply call P out of this domain, and given some parameters theta. And then normally, when we now look at this probability P of D of theta, this is given by independent. We are assuming that these x's are independent and identically distributed. And we would typically then have So I'm trying to distinguish between the uppercase letter and the lowercase letter for the individual events. And what we typically want then is to find the optimal theta, which is the maximization of this probability of theta, which is normally a real parameter of this probability P of D of theta. Now, this is actually, from a computational point of view, since we're dealing with products, this can actually lead to numerical inaccuracy, because in cases where the probability is very, very small, so if you think of the different events here, which are multiplying with, you can have cases where the probability is extremely small, and then you will simply have probabilities which could be large, which are then multiplied with the many numbers which are close to zero. So that can easily lead to a loss of numerical precision. And it's also a little bit more clumsy to calculate the gradient of this quantity here. So the equivalent problem is that you take the log of the probabilities, because then this changes into a sum. So if I take the log of the probability and rather optimize that one, and we know that the log is a monotonic function. So if it's a positive one, this becomes a concave problem and a maximization problem. If we prefer the minimization problem, we can put a minus in front of it. So the log of this P, this is the problem which we would typically optimize. We know that this simply becomes a sum over I equal 1 up to n of the log of the individual small probabilities. And then we would optimize that quantity so that what we end up optimizing is actually this function, d theta of log of P of x of theta. And this is the one we want to drive to zero. This function here, this gradient, if you go into textbooks in statistics, this is actually, it has a name, and it's called the score function. So when you have the optimal parameters, then the gradient of the function you're optimizing should be equal to zero. So you will often see that this is called, in a statistics connections, this is called the score function. Now it has some interesting properties, because we can then use it. If we take the second derivative of it, we can actually define something which is called the variance. And this variance is actually interesting for us in many different connections, because it's going to define the Fisher information. So this score function here, if we now look at it, this is actually this derivative of the log of P of x of theta is actually given by 1 over P of x as a function of theta with a given theta. So you could actually rewrite this one also like this. You will see that often in textbooks. So this reads the probability of x given theta. And theta are the parameters we want to optimize. And you see that this one is something which we can actually rewrite as P of x of theta with derivative with respect to theta. And then we have a specific value of theta. So that quantity is actually interesting because it measures a relative sensitivity to the value of P. And the P, if it's very, very large, then clearly the sensitivity will be, or this quantity will actually be small. Now, this is also an interesting property, because if I now look at my probability, if I look at this, if I now integrate over all the x's, so x element in this domain as a function of theta of d of x, this has to be normalized to 1. Now, I can actually rewrite this one. So because what it means is that if I take the logarithm of that specific quantity, so I can actually rewrite this one in terms of another quantity. So we know that this is equal to 1. So I can rewrite this in terms of, when I take the gradient of it, of d theta of this quantity, and it's actually not so difficult to see that that is the case of d of x. this is going to be the same as the gradient, the expectation value, with x drawn from this probability x of theta. And then I have some parentheses in here, and this is given by d log of this function p, and I'm suppressing the dependence on the x and theta in the function here. So it's actually not so difficult to see that. So this quantity here is actually a mean value. If I use the identity this is an important identity, where I use the fact that the probability has to be normalized. And if I take this derivative, I can actually show that this is one important identity. Now, and so this is something which I will call the first identity. So this is identity 1, this expression which you see here. There is also another identity which is important for us in this case, and this is something we will label as identity 2 here. And the derivative here, the second derivative, so this is an expectation value, and x is now computed according to this model which we have for the probability. So this quantity here, the log of p with respect to theta squared, is actually equal to minus, and this is the expectation value, and I leave that as a small exercise to show. You will also find a guidance on how to solve it in the additional notes. And this is given by the second derivative of log p with respect to theta. Sorry, that one. Like that. So this is because since the mean value, which we had in the previous identity, identity 2, identity 1, is 0. Now, this quantity here defines the Fisher information. So if I go back now, the interesting thing, if you now look at this expression which we have here, this is actually the derivative of the log. So this is nothing but the log derivative. If we then scroll back a little bit to what we did here last week, we defined this quantity O of k as the derivative, the log derivative of the wave function. So if you now think of the VQE, this O of k here is actually the log derivative of your variational ansatz in the variational quantum eigensolver. And the thetas are the rotation angles which we set up in the circuit, which then is optimizing the theta by a classical optimization method. So what we did then was simply to define those quantities. So the main difference here, when you look at this quantity which you have here, if you think of psi, the quantum mechanical wave function, squared, which is a probability. If you now take the wave function squared here in this equation, if you take that in here, if you square it, the only thing you get then is actually a constant 2 in front of the log of psi. So that besides a constant of 2, the quantity which you see here is actually pretty close to what we defined here. Okay? And this is actually what defines the Fisher information matrix. So if you now look at this identity 2, which we have here, this quantity here, this is actually, if we now call if we now define these quantities O of k, which we had, so if we now look at this d log of p of d theta, and we had a quantity K here, if we now go back to the comparison which we want to have with what we did last week, you see now that we defined this object O of K. So the thing which I'm going to do now is simply to define that one as a quantity which I will label as an S of K. And the reason for why I call this S of K is that I defined the score function. So the S stands for the score function here. And this is the quantity we want to drive to 0 in the training. So when you have found the optimal parameters theta, it means that your score function is identically equal to 0. Okay? So if I now take this second identity, which I have here, I can then actually define the covariance of these quantities, and keep in mind that the mean value of this quantity is actually equal to 0. So this becomes important for us now, because I can now define the Fisher information matrix which I define as Fij, and this is classic. You will find this in standard textbooks in statistics. I mean, more advanced courses in statistics, obviously. And this is given by X, which is now drawn from this probability, which we have. And it's the covariance of Si and Sj. And this is the same as the quantity which you see here. So this is actually the covariance of X with respect to this quantity, this probability distribution which we have of the quantities Si and Sj. This is typically often the way you write the covariance. And this is the same as the expectation value of X, of P of X, of theta. And then it's given by the second derivative of log of the probability with respect to theta I and theta j, the parameters which we're optimizing. Now, this quantity can then be used to define a measure and a metric, which is used in the optimization problem. And so this Fisher information, what I'm going to do now is to jump into those slides, which I have added to the lecture notes in this week. So let's do that and take a look at the final discussions of this topic. So I have, here we go. So the slides which you see here contain actually a summary of many of these arguments, but then linked to both stochastic reconfiguration, which we discussed last time. There is also a discussion why we use log of P, log likelihoods and the score, and then the relative sensitivity, and then the kind of relation between the Fisher information matrix and the quantum Fisher information matrix, and how these natural gradients pop up. And then there are some bounds, and one of these bounds is called the Kramer-Rao bound. So the first part here is actually what we did last week. And actually in these slides, I used alpha instead of theta. So I'm sorry, I'd forgotten that I'd been using alpha, and I mix sometimes notations here. So this is the way you would update the parameters with the stochastic reconfiguration. And this stochastic reconfiguration is actually a quantity which is equivalent with this Fisher information matrix. So in the second part of this additional material, you will find a discussion of both the score function, which we mentioned now on the whiteboard, and the Fisher information and the equivalence with that approach. So typically, this log P of X then is a very important quantity, because you will see this. So I'm trying to catch many birds with a stone, because when we move to Boltzmann machines, we're actually going to optimize log P of X, because we train a probability distribution. And when we do quantum mechanics, we're actually training the wave function, and the wave function squared gives us our probability. And you will find this in the maximum likelihood estimation, the Fisher entropy. You have many other different quantities which appear in machine learning. So probabilities multiply while optimization prefers additive structures. So the log is actually an important property in the optimization of probabilities. So if you think of this without linking it with quantum mechanics, this is actually a quantity which you will encounter in many optimization type of problems, especially for generative methods. If you're doing Bayesian statistics, also if you do statistical mechanics, you encounter the Boltzmann distribution. So this log P of X is actually a very important quantity, and this is roughly what we put up on the whiteboard. So these are the quantities which we want to train. So maximizing the likelihood and the log likelihood equivalent. And the log likelihood is far easier to work with analytically and numerically. So if you want to dive a little bit deeper into it, take a look at these nodes. This is actually something which we have defined, so I will skip that one. And I also skipped these identities because we had them on the whiteboard. But these define the Fisher information. And typically the kind of information content, there's another thing which is important. In the beginning of this course, so I'm using this also to repeat some elements, we actually define the von Neumann entropy, which is the quantum mechanical equivalent of the Shannon entropy. And the thing which is also interesting is if we have independent events, which we often assume, then the probabilities can actually, when we take the logs, they become additive because the log of the product becomes additive. And if you look at the entropy, this is normally what we call the expected information content. And this is nothing but actually the expectation value of this information content. So one of the reasons why we use this one is simply because if we have a very rare event, that means that P of X is much smaller than 1, then log of that quantity is a large number. So that means unexpected gives a large value. The expected one, where you have P of X equal to 1, so you know exactly what you have, then log of 1 is 0. So this is just a way to characterize the information content. And this is a quantity which we have been used to study entanglement. And if you think of the connection to statistical mechanics and machine learning becomes important for us because this is the typical probabilities which we would train when we have a generative methods. So I'm setting this up because this is something we will come back to when we are going to look at the classical Boltzmann machines and the quantum mechanical Boltzmann machines. And many of these generative models, they are actually built on log probabilities. So you will encounter that if you take a course in generative methods in machine learning, like variational autoencoders, Boltzmann machines, etc. And Boltzmann machines are very popular ones in machine learning, and they have their quantum mechanical equivalent, which is, to me, I have to say I'm a little bit biased here because I've been working with Boltzmann machines, but the quantum Boltzmann machine has a lot of fascinating mathematics. So this was a small digression, but the thing which is important for us is actually this Fisher information, which we defined in the lectures. So we have the score function, and because the mean value is 0, then we can define this Fisher information matrix, which is then just given by the expectation value with respect to this probability of the second derivative. So that gives us, so the curvature of the log likelihood means that likelihood surface is sharply curved around the optimal parameters. Its distinguishability, if you have a large one, means that nearby distributions are easy to tell apart. Now, there's something which I will not go into, but you can actually define a metric here, which means that, so this is a metric which defines the distance between distributions, and this will be the quantity you would optimize. And when you optimize a quantity, I'm going to skip that one, you get something which is called the Fisher-Rao metric. And the score function defines the tangent vectors to this manifold. So this is a probability distribution which forms a curved statistical manifold of parameters. So this measures actually how the information content of an observation changes with model parameters. And clearly, the reason why you take the log is because that transforms a positivity constraint and normalization into an unconstrained, geometrically flat coordinate system where gradients measure relative changes. So there's a lot of interesting mathematics, which if you have taken a course in advanced statistics, you will actually encounter something like this Fisher-Rao metric, which is actually given by now the second derivative. So if you make a Taylor expansion of something which is called the Kullback-Leibler divergence, you will actually see that the second order term, because the first order term disappears because the average is 0, then you will actually find this as the optimization problem. So when we did the variational Monte Carlo, what we had then is that we were differentiating the probability norm, the wave function. This is the norm of the wave function. And then we had a derivative of this quantity, which defined this quantity here. And then we had the score for the variational Monte Carlo calculations for the energy, which is given by this quantity if we have a real wave function. And the score is the centered logarithmic derivative. And the same object that enters the stochastic reconfiguration we discussed last week through this quantity is actually the same thing which enters the Fisher information. So in that specific case, the Fisher information is actually 4 times this function which we defined last week. And when we do the study this metric, the natural distance on a quantum space, that gives the same result. And for real wave function, this is the quantity we want to optimize, confirming that this, the stochastic reconfiguration term, governs both the quantum distance and, if you're looking at statistics, this Kullback-Leibler probability, then this defines also the relevant distance there. So it means that if you look at the natural gradients, what you're optimizing then is this problem here, subject to this one being given by a small number. And then you have a Lagrangian multiplier, and then you get that with a natural gradient, this is the optimization problem. So plane gradient descent is actually a special case where this f is equal to 1 and you have a parameter eta. So the natural gradient is a quantity which appears in a standard statistics definition, but you can link that one with the stochastic reconfiguration. So you have the natural gradients in statistics, you have the quantum geometry, you have the natural gradient, and then if you want to look at the connection with a standard variational calculation, it's just called the stochastic reconfiguration. So these are the quantities which you can then use in the quantum machine learning optimization, which we are going to look at after the break. So I went a little bit over time now, but after the break, instead of us doing a standard gradient descent where this matrix is put to 1, we're actually going to implement the quantum Fisher information, which is given by this expectation value. And this is something which normally is a little bit more, requires more cycles to calculate. But you will get a gradient which is then determined by the derivatives of the wave function. Okay, so there are some additional things here, but I have some summary here of different terms, or different things, which in a way involves also a lot of statistics. And if you're not too familiar with it, the thing which is important is that if you want to take away a message from this, is that the Fisher information matrix can be used to evaluate the Hessian matrix. And that carries information about the wave function. And it gives normally, when you replace the standard learning rate approach with different optimizers with a natural gradient, you're actually guiding the optimization problem according to the way the wave function looks like. So you're baking in the right physics information. And in our case, this wave function is the variational ansatz, which we are setting up for the quantum circuit. So after the break, I wanted to discuss some. So what I wanted to do now in the second lecture, before we move over to Boltzmann machines, classical and quantum, is actually to go through some of the codes which we did discuss the theory of, but we never looked at implementations. So there is a Jupyter notebook from week 14, and there is a Jupyter notebook from week 15, which is the last week. And what I wanted to do is actually to just say a little bit about some of these implementations. Now, the lecture notes from week 14 contain also a link to things which we have been looking at before, like the HHL algorithm, the VQE, etc. So in a way, it serves to summarize many of the methods which we have discussed before. Now, the thing which we will pick here is just the quantum neural network. And as we said, the quantum neural network is actually something which is a parameterized quantum circuit. And it's normally, the normal implementation is something which we call a variational quantum circuit. And the quantum neural network here is actually a variational quantum neural network. So the quantum neural network, as we said, we have a implementation of the encoding of the input, the quantum embedding, and then we have the variational circuit. So typically when we are set up such a network, we need first to prepare the initial state, as we discussed. And we would typically, in the codes which you see here, we will treat the initial state of the system just as a tensor product of qubit zeros. And the example which you will find below here is actually an example with 2 qubits. And the reason for that is that this is something which is run in just some few minutes, or actually less than a minute. If we add more qubits, this is going to take much more time. So feel free to explore these codes and play around with them. So the unitary here is normally set up as a composed of rotations, and it depends on the type of data. And the variational circuit is the one which we build as layers of products of rotation matrices, which then include Pauli matrices. And then the output is simply this function here, where we have a specific observable on the final state. So this is our network. We have the encoding, we have the variational part, and this is the final expectation value which we calculate. So the QNN, which we deal with, is something which we would call a variational quantum state. So what we're optimizing is actually this function here as a function of these parameters theta. Keep in mind now that the embedding or the input encoding is always something which is free of parameters. And it's pretty common to not have any kind of entanglement there. So this is just a product or a tensor product of different rotation matrices, typically Rx. So we have the feature map, and we can have a feature map. It can also be included as a Hamiltonian evolution if you want to. This is also one way of doing it. So there are many, many ways of doing this feature mapping. And then the Pauli ansatz, the Pauli expansion of the ansatzes are simply having a set of Pauli matrices plus some matrices, two qubit matrices which entangle the qubits. And then we have the Baker-Campbell-Hausdorff, which is often used to expand the functions. So typically, we consider 2 qubit case. This is the one we have here. There's a simple encoding like this one. And then if you have a variational layer, you would have 2 parameters here, and then you have a CNOT gate here. So you would have a rotation on both the 2 qubits, and then you entangle things with a CNOT. So this could be the simplest possible circuit which you would deal with. And then, so we apply this RY on each qubit, and then after applying that one, we measure Z.I on qubit 0. And then the output would be something like this. And then this f of x is compared to the target in a cost function for optimization. The key element then is actually this transformation here, simple encodings like user rotations, and then the set of different Pauli matrices which enter the rotational part. So the example which we have here is an example which is a simple feed-forward quantum neural structure. So we have the embedding layer, we have the variational layer of L blocks of parameterized gates. So every block then defines a layer. And then each block may actually, as I say here, act on all or subsets of qubits. And you can think of each such block as one layer of a standard neural network, if you want to make a comparison here. So there are several examples here. And in the example which you will see, this is what I am going to encode. So I'm going to optimize the mean squared error. This is the first example which you will see. And the other example is a variational classifier, where a binary classifier can output either qubit 0 or qubit 1. So there are two examples which follow here. One, which is a standard mean squared error problem, where we are trying to fit a function. And we know the function values, y of I, and we are trying to then make a model, which is our neural network here. We can also do a variational classifier. And if we now look at the functions, when we are calculating the gradients are then calculated by the parameter shift rules for all the parameters. And this is the expectation value. So this is exactly what we did when we had the VQE, because then we just replaced this V with the Hamiltonian, which we have at hand. So the parameter shift rule, as long as we deal with all these nice Pauli matrices, we have an analytical expression here. And if you look at the code examples, the parameter shifter rule is actually implemented directly, in this case in PyTorch, and to differentiate the classical simulation. And then the optimizers, you can use gradient descent or more advanced ones, so the code which you see here is in a sense written from scratch, but it uses Torch, PyTorch. And the gradients actually, they flow through the classical loss into the simulated quantum circuit via the parameter shift trick. So we have exact expressions for the gradients, and then we are ready then to set up. The thing which is not included in here, in these examples, is actually a comparison with the quantum Fisher information. So in the slides for week 15, we implement that one in the optimization. And then we have this metric. So that means that the parameters which we are looking at is actually given now by the quantum Fisher information multiplied with the gradient of the function we are optimizing. So in our case, the gradient of the function we are optimizing for the mean squared error problem, which we have, is this one, a standard mean squared error. So for those of you familiar with neural networks, this is just a kind of variant of a neural network, except that we have a network which is actually much more shallow. So I'm going to just go through the example here. So this is just a discussion of how to avoid barren plateaus. I will come back to this, but this now contains, so we simulate a 2-qubit variational quantum classifier with using standard Python libraries. And the quantum state is represented as a complex vector of length 2 to the n. So we are going to, and the unitary gates are typically 2 to the n times 2 to the n matrices. And gradients are then calculated with a parameter shift rule, and then implemented manually, and then they are wrapped into a torch grad function, so that PyTorch's Adam optimizer can train the circuit parameters. So we have a regression demo. This is the one which I will just go through now. I will skip the classification one. I invite you to take a look at it. And as I said, all simulations use PyTorch for the regression demo and pure NumPy plus Adam for the classification, and also the QAOA demos. So there is no specific library which is required. So here's the network which I'm setting up. So I'm doing a classical neural network, which is a dense one. So, and I'm going to fit a one-dimensional function. So the function we want to fit is this one. So we have f of x given by a third order polynomial, and where we also add some noise here, which is then given by a Gaussian distribution. So x lives between -2 and 2, and this is the function we want to fit. And we are going to make a classical neural network where we have the input. So there's one input, the x value, and there is obviously one output. And we set up a neural network which has 3 hidden layers, 32 nodes, and 16 nodes in the final hidden layer. And this is the output layer. And we use tanh as an activation function. And this gives in total, when you add up everything, it gives 1,649 parameters. And then I train, so obviously we are training this for many points. So we have, if you have 100 points, you would actually have an input matrix, which now has dimensionality 100 times 1. And then the quantum neural network is just 2 qubits, and I have 4 layers with a re-uploading circuit. So this gives me 34 parameters in total. And the typical parameters are then given by the cosines and the sines which enter the rotational matrices. So I normalize my data to -1 and 1. To do here. This is especially important for the QNN, rotations, angles. This is something to keep in mind. So I define my data set between -2 and 2. But then when I'm looking at rotation, the angles are sensitive to input scale. So this is something to keep in mind when you're using a quantum neural network. So I do the split the training. So I have 150 training and 50 validation points and 100 test samples. This is the setup of my data set here. So here is just me setting up the data set. This is a classical setup of a data set. I normalize the data like I've discussed here. And then I plot the data. So this will be the data which I have. So this is the function without noise. And then my training data are the points which you see here because I add some noise to it. So the training points are which I use then, because if you take the true f of x, that is without noise. And this is often also much simpler to train. So the classical neural network has a simple architecture. So I have tanh throughout. This is the width of the hidden layers. And this is actually pretty, as I said, generous for 4 coefficient polynomial. So in a sense, it's actually you could get away with one simple layer. So it's not a fair comparison with a quantum neural network here, because I'm actually making it a little bit too large. You will see that if you play around with a smaller network, you would actually get a pretty good description of the data. So what you have here is the feed-forward neural network. So this is the feed-forward pass. You have the tanh function, and then there is a backward part. So MLP stands for multi-layer perceptron. And I initialize the weights, so normally distributed. I count my set of parameters, and then I run my code. This is the setting up the network. And then I have a quantum gate library. So I've tried to make this as simple as possible. So this is the way I would encode the inputs. And I have my RYs and RC. These are the different data for the variational part. And then the simple qubit gate embeds a 2x2 gate into a full 2n dimensional Hilbert space. So you will see here the definition of the different gates, depending on the angles which we have. and then I embed the gates, and I also have a C0 gate in order to entangle them. So if you want to play around with here, you could actually take and await the C0 gate and see what happens. What you will see then is that the expressivity or the capability to actually parameterize this function is less good when you take away the C0, when you don't entangle. So that's a kind of numerical experiment. If you want to play around with it, you could actually do that. So this is just the setup. So you can see some tests here, which where I simply test that things are going correctly. So I encode the quantum layer. So this is the encoding part. So I have this on each qubit. So with a learnable scale W, I rotate and then I entangle. So this is my QNN for the forward pass. This is now the entangle plus rotation, and this is the encoding of the data. And the dates are 2 qubits. They're prepared in the state 0, 0. And the function which I'm, the Y data is now given by alpha times the expectation value of Z0. And Z0 is simply us collecting all the expectation values of all the results which we get. So these are additional trainable output scaling parameters. So when I run it through the network, you can now see that the QNN has in total 34 parameters. I have 2 qubits and I have these 4 layers. The state dimensionality is 4. So the layout is actually 4 layers times 2 qubits times 4 angles plus 2 outputs. And that's 34. So these are the total parameters which I have. And what I've done here is actually to have a optimizer as Adam. So there is no natural gradient here. So feel free to add that if you want to. I set up the learning rate, which I've been using. I also been using a learning rate for the quantum neural network. And you can switch between just a standard gradient descent, or you can actually, if you want to, you can then replace that with Adam in the implementation here and use the Adam optimizer. So that's a pure NumPy implementation of the Adam optimizers. And they have the ML, the loss function, which is my mean squared error. And then I train my network for the different parameters. And I train my QNN, same thing. And then at the end here, when I look at the training of both methods, you will see that my classical neural network takes very few moments, whereas the QNN took me, actually in the last calculation I ran, it took something like 3 minutes. You can see the results here. So I start with my NumPy feed forward part. I use Adam. And you can see now how the mean squared error on the training data drops. It's 0.02 here. And the validation error is also more or less on the same level. And you see clearly here that even if my neural network has less parameters, it takes more time to train here on my CPUs here. And you can also see that so this is the total time which I use, 1 second towards 1800 seconds. So clearly running this on a classical computer is actually not optimal. So you're probably not impressed. And even the mean squared error is actually not very good compared with the one you get from a feed-forward neural network, which in this case actually has an overkill of a number of hidden layers. So you will see if you play around with this code, if you just replace it with 1 hidden layer with even 20 hidden nodes, you will actually get a pretty good result. So the MSE is actually something like an order of magnitude worse, as you can see here. The validation test is not that bad, but clearly, if you cannot run this on a quantum computer, it's perhaps not the the best one. But clearly, the number of parameters is much smaller. So this is clearly the quantum advantage. which you would be able to realize on a quantum computer. And for 2 qubits, this algorithm is something you could implement on many of the available quantum computers, which we have access to. And there's a visualization at the end here, where we look at the fitted curves, and you can now see the training curves here with the mean squared error. So they seem to flatten out as a number of epochs, but you still see that the standard multi-layer perceptron, the classical one, actually outperforms the quantum neural network. So I haven't run these codes on an actual quantum computer, but for those of you doing quantum machine learning with quantum neural networks or project 2, this could be something you could try at the end of the project. So run it classically and then run it on a quantum computer, like using Qiskit on the IBM machines. Okay, so this was the example I wanted to discuss. If you scroll down here, you will also find a classifier, which comes down here. So there's a classification experiment where we are looking at a binary classification problem. This is pretty similar, and you will get much of the same results. But the one which I wanted to say a little bit more about now is actually the one from last week, where we actually looked at the solution of partial differential equations with, again, variational quantum circuits. So in this specific case, we have been looking at both classical pins and also a quantum pins. And in this specific case, we started with the the Poisson equation, because this is something which we also discussed in connection with the HHL algorithm. So if you want to, you could take these examples and compare. If you're doing the HHL algorithm in project 2, you could actually compare the Poisson solver here with the quantum pins with the one you get from the HHL, which in that case is a pure quantum algorithm. There is no hybrid part. So here, on the other hand, we have a variational quantum circuit. So again, the basic machinery, if you go into the weekly slides from last week, you have a encoding part, you have the variational part, and then you have the initialization of the system. And you have some observable, where you typically could measure one of the bits, so you could measure all the bits, all the qubits, and then you calculate this expectation value. Again, the parameter shift rule is the same, but we have now in one of the codes, we have actually included what is called a natural gradient. And you will see that in the example here, in section 9, there is an implementation of the quantum Fisher information. There are also additional applications, but I will not discuss every case here. But I wanted to focus on the one for the 1D Poisson equation and the section 9 here for the quantum Fisher information applied to the Poisson equation. So that means that you will see 2 cases. One where we don't use the Fisher information, but we replace simply this F with a learning rate. And then we call either a standard gradient descent, or we have the Adam optimizer or root mean square propagation, or any of the more popular optimizers. So the interesting thing is also that this variance of this quantity is actually the one which leads to barren plateaus, and that's normally proportional to 2 to the power of n inverse number of qubits. So if you have a very deep circuit, then clearly you can reach this area with a barren plateau. So the problem, as we discussed last week, is a problem which is often nicely defined. It's a minimization or maximization problem. But due to the depth of the circuit, we can actually get a variance on the cost function, which then leads to these barren plateaus. So the typical approach then is actually to use a shallow network, which clearly then leads to less parameters. but at the same time, you have perhaps less expressivity. Actually, the topic of barren plateaus is a very active research topic in quantum machine learning. So the thing which we did, and this is also listed in the slides for last week, is typical angle encoding, which is one of the more common ones, which is used when we then want to implement the initialization of the data, or the feature mapping, or the mapping embedding, as we've been calling it. And then we have the standard, the parameter shift rule, and also for the second derivatives, we would have this derivative rule, which you see here, which is just a 3-point formula. And that leads to 3 circuit evaluations for the Laplacian. So there are no ancilla qubits here. You can also use Fourier theorem and have a QNN output in terms of a partial Fourier series. You have data reuploading and the encoding comparisons for the typical PDEs, which are included in the code here. We have the angle encoding, the reuploading, amplitude, etc. We need to define the gates again, like we did previously. So we have the different gates here. We have the RY, we have the C0, 01, C0, 10, etc. So these are the typical gates. We define the layers, which these are the variational layers with 4 parameters active. So the typical structure here is a C0. We have a rotation here. So we're actually setting this up as a 2-qubit problem. So we have a 2-qubit QPIN circuit again. And we are setting up the boundary conditions. So we have actually a function where we now are plugging in the boundary conditions. And this is given by standard Dirichlet boundary conditions. So we have an implementation of spatial derivatives. So we're actually solving Poisson's equation here. So we have the second derivative. We have the first derivatives. This is the first spatial derivative, exact per qubit parameter shift rule. And then we need the second derivative, which is then via the central differences. And it's exact enough for the QPIN training. So keep in mind that we are solving a differential equation with first derivatives and second derivatives. And we need to encode them. So we have here's a vectorized second derivative. There are just some tests here that the derivatives are being implemented correctly. So there's a visualization just here, which it's not that important actually. And there is a Fourier analysis of the quantum ansatz. So we have an pi times x encoding, and the output is periodic with a period 2 in x. And typically the frequencies which you have for 2 qubits are 0, 1/2, and 1. So we follow a recipe by Maria Schultz here from 2021. So just, you can now see the QNN output over 1 period, but then we have the classical physics-informed neural network. So we have the residual here, that's the difference between the left-hand side and the right-hand side. And then we are baking in the boundary conditions. So we are solving Poisson's equation, where we now have a second derivative, which is equal to a function, and the boundary conditions, which are then given by standard Dirichlet boundary conditions. So in the calculations here, we use autograd for the classical pin, and we have the parameter shift rule for the quantum variant of it. And we can use for the optimization geometry, we can use the quantum Fourier, the quantum Fisher information. But in our case, in the first run, we're actually comparing that with a standard usage of Adams. So the ansatz is this one. So these are the function we are going to optimize. We have for any gate, we then have the parameter shift rule. We have for linear PDE operator, this is the quantity we need to evaluate. With D, so both shift rules commute with D, and this makes the QPIN training tractable. So the QPIN loss function is given by the function here, as in the classical case. And the total cost per gradient step is actually given by the number of points which we are looking at. And the NP, I have to remind myself what NP is actually. The number of points we're dealing with, sorry. So this is the problem we are looking at. So the loss function is this one. The second derivatives are then calculated via the input shift. So this is a 3-point rule for the approximating the second derivative. And then we have the Dirichlet boundary conditions, which are enforced exactly. So this is just the boundary condition. You can have a Ritz loss, which is also another possibility where you would have parameters to optimize here. But let's just focus on the standard way of doing it. So we have an exact solution, which we will compare it to. We have a right-hand side of the differential equation. If we go back to the equation here, this f of x is given by, in this example, pi squared times sine pi x times the wave function. Pi squared times sine pi x, and the exact solution is actually a sine pi of x. So this is a case where you actually have exact solutions, which you can then compare to. So I do the pins calculation in here. You can see now this is the training of the quantum pins, and you're actually getting pretty good results. So the loss function then is close to 0. And I plotted the results here. And basically the quantum mechanical pin, when I use Adam in the optimization, is giving pretty good results. And on the scale which you see here, there's basically an exact wave function and a Q pin with a learning rate, with a norm 2 hyperparameters, which is put to 0. And it gives actually for these 20 points here, it gives a result which is pretty close. You can see the error is actually for the different points. Obviously, at the end points, you have encoded the boundary condition, so then it has to be 0. But then the error is typically on the size of 10 to the minus 4 to 10 to the minus 5. So keep in mind that this point here, the 0 point, there we have encoded the boundary conditions. And there the function, we require the function to be 0. And this is a training loss with Adam, and it's doing pretty well. Now, the thing I wanted to go down to, so there are some intermediate examples with a harmonic oscillator, and you can take a look at that one as well if you want to, where compare the exact solution with the Q-pin solution. You can see the training loss. There's also an example with a heat equation. I'm not going to go through that, but I wanted to show you the implementation of the quantum Fisher information. Now, one of the things you end up when you have this function here is that this function can actually exhibit zeros. So what's pretty common to do then is to add a non-zero and small parameter epsilon. This, for those of you who have taken a course in machine learning, this is what you would normally do in ridge regression. So you add a hyperparameter, which then is meant to avoid the possibility that you have a term which in this Fisher quantum information, which is actually leading to a matrix which cannot be inverted. So, and the problem is that when you look at these residual losses, they can actually create highly non-isotropic gradients. And this kind of preconditioning aligns the update with the geometry of the quantum state. So the same set of functions, basically, but we now encode the natural gradient, and this is given by the Fisher information, which is then calculated in this function here. And when we do that, we also make a comparison with ADA. And you can see now that the natural gradient actually behaves pretty well. And here we are getting an error at the end after some 200 steps here, where the error is down to 10 to the minus, roughly 10 to the minus 4. So keep in mind that when you use Adam as an optimizer, you're not being guided in the optimization by the shape of the wave function. When you plug in the natural gradients, what you will often see is a benefit, which although it requires more computations, and you will see that this is computational heavy, you're actually getting a result which here in this specific case and gives a slightly better loss than you got with Adam. So you could, if you continue this now to 500 steps, you will see that both these curves will flatten out. And you see now if you go up again a little bit and look at the calculation with only Adam, which is it's a much cheaper calculation. You can see now that here I went to 300 steps. So Adam in this specific case, when it reaches 200 and beyond that one, it gives a result which is basically independent of the number of steps, and it flattens out. So in here, I just went to 200 steps because it was pretty time consuming to calculate the quantum fissure. But in general, the result you will see, even if it's more computational, requires more computations, is that it often gives a better result. Okay, so the last lecture next week, I'm just going to briefly say something about the topic which we announced for today, which was actually Boltzmann machines, classical and quantum. I just wanted to say a little bit about it, but then we will spend the time next week to discuss the projects and to do a summary of what we have done. But probably now, as we've been repeating these keywords of variational quantum circuits, this has been the main theme in this course. The variational quantum circuits, which allow us to implement hybrid algorithms, which include an optimization part and a standard quantum computing part. But we've also looked at how we would do this with the QPE, which also led to the HHL algorithm. But the main activity focuses a lot around implementations of hybrid algorithm, although quantum error correction algorithms have now become so good that you can actually run, with quantum error correction, you can actually run the QPE algorithm on quantum chemistry problems, which would be something almost unfeasible for just some 10 years ago. Okay, let's stop here